next topic is digital links. Right. So when it comes to the concept of digital links, uh, the simplest possible link we can achieve is in the form of a point-to-point link. Right? You have the point which is the information source, right? And you want to send that information which is in the digital format to a destination, right? So something like this is a point to point. Okay, this is P, this is another P, so which is called as the point to point. Right. So when we say we are trying to implement a digital link in terms of a point-to-point communication, right? On one side, you are going to have a transmitter on this side and a receiver on the other side. Right. Now, the simplest, we'll try to write a very simple block diagram first. Okay. Then we will try to update this. Okay, so let's start with a very simple point to point link, which is a digital link. Now we have the first block, which is the information source. Right, that's the first block. Then you have the second block, which could be the transmitter itself. So when we say we have a transmitter over here, this actually includes the coder, right? The information which is coming in any format, maybe analog or maybe it is already converted into digital, right? Doesn't matter which format it is, but you have to convert that into the using appropriate coding, right? Coding, then followed by you have to use some filters to restrict your frequencies. Okay, you may have to apply channel coding, perform the quantization, etc. Many things are included in the transmitter, and uh, including modulation, analog or digital. So since we are discussing about the digital link, we can assume that we are discussing only about the digital parts. Okay, so it's a digital modulation techniques are also included in the transmitter, right? Then the channel comes into picture. So the channel will deliver the message which is sent from the transmitter to the receiver. Right. So this is the channel which connects this transmitter to receiver. Right, this is the channel. All right, so then this message gets delivered maybe to the user. All right, so this is the most fundamental block diagram of a digital link. Right, now In order to design such a link, uh, basically many variables are supposed to be considered, which are interlinked with each other. Okay, like for example, let's take an example of optical fiber, which is a very good example for a digital link. Okay, so I'm accessing internet through digital fiber, okay, optical fiber, for example, so, to be specific. Like anyway, somewhere we have a information source which I want to access that using the internet, right? I go to the website and I type the web address and the web page, right? In order to open that web page, basically that information which is present somewhere, it is stored in the form of maybe a binary data or info image data or audio, video, anything, right? In some server, right? That gets modulated in their transmitter side and will be transmitted in the form of light. Okay, it comes to maybe very close to the, maybe it comes into the network device which is present in my place, and that converts the information in the form of light into the required binary or digital format, right? So that's the receiver and I'm the end user in this case. So we can see that this is the overall structure of a digital link. And in such case, what are the requirements, what are the variables that needs to be considered in order to design such links, right? That's what we are going to discuss today, right? So for example, maybe the first thing which we have to decide is that what is the type of information that you want to send, right? That by default, as of now, we are restricting it to the digital only. So obviously, you can eliminate that point. The type of information you want to transmit will be digital in nature. Okay, that's fine. Then, what is the component that you are going to use in the transmitter, right? So one important aspect is the on the transmitter side, you will decide something like what is the source, in the sense if I'm considering the light source, right? I should be very specific about what is the power of the light source. It should be sufficient that it carries the information through a certain distance, right? For example, it may be it is required to transmit the data for 100 kilometers, so your power of the source, right, should be sufficient for that reason. Okay, so that's the first point. Then similarly, even on the other side, that is a receiver. On the receiver side, I might have to specify the detector, right? In case of if I'm talking about the light source, I need a good photo detector, because I know that after a long distance, the what you call, there will be a lot of disturbance in the signal, right? Addition of a phase shift, or you may lose the data, right? And you may lose the what you call magnitude, okay, voltage, right? That may be reduced, attenuation, etc. Many things will happen, so you should have a good photo detector in terms of the detecting characteristics, how much it is, uh, how good it is to respond to light, right? So that's what is important here. So on the receiver side, I might need to decide about the detector, its characteristics, right? So before this whole link works very in a very fine fashion or very properly, right, you may end up doing, say, several iterations, right? So that's what is the common thing about this design process, right? Now let us look at the what are the major system requirements. Okay, the first one is you have to decide. So first, let me look at the parameters. Parameters to be decided. Right. The first one is the desired transmission transmission distance. Depending on that, the first two points I mentioned definitely will change, right? If it is just 5 to 10 meters, I may use simple LED, right? But that may not be sufficient. When I go for a larger distance, I might have to shift from simple LEDs to say lasers. Okay, so like that. The second important characteristic is that what is the data rate? Like what is the minimum Mbps you are expecting, right? It's not Mbps. When it goes to light, it is Gbps, right? Fine. So, but still, what's the data rate? It, in other words, you are actually talking about the channel bandwidth, right? At it simultaneously, how much messages can be transmitted? That's what is a bandwidth is all about. Okay. Then what is the expected error rate? I will simply mention that as BER, bit error rate, right? You send 1, you receive 0, you send 0, you receive 1, with what probability, right? So that is the error rate, right? These are the basic parameters I have to decide at first. Okay, my transmission. True. Yes, true, absolutely. That's perfect, right? Satellite link is also another very good example. Okay, all right. Now, in order to once I decide these three, like I want to communicate 100 kilometers, this is my data rate, and this is the expected bit error rate. Once you decide upon this, now we will, in order to fulfill all these requirements, a designer has to choose, right, the specific type of uh, components, right? The components can be chosen based on the following. Okay, so I'll write something like this. So to fulfill the requirements, so designer can choose the components. Right. Now, what are the options, right? The designer has. Okay. Right. Maybe it's about the capacity. Okay. So the capacity of the channel. So I'll simply write a channel. Right, appropriate channel needs to be chosen, right? It actually based on, right, the channel. When you choose it, actually basically you are selecting specific channel that is suitable for your requirement. Like you may choose light, right? For example, if you go for optical fiber, the if you don't have an option like satellite, you may not have many options available. You have to use a free air itself. Okay, but if it is something like communication between two continents, right, you may have many options, right? You may use microwave, right? Or even satellite links, right, etc. You have many options. Or if possible, if there is a if the optical fiber exists, definitely you can use it, right? So something like that. So the channel has to be chosen first, right? Using what you are going to use. This actually includes the response of the channel, right, to the specific type of signal. Maybe again it is digital signal only, but uh, we have chosen a specific type of modulation, right? We might have chosen a specific type of modulation for our purpose, right? In order to achieve that and get a good communication link, it is always necessary that you use a specific channel. So for example, I'll come to, let's say that you have chosen something like maybe see, you have chosen, I'll write an example. We have chosen the light communication. So this is called as visible light communication, VLC, right? In such case, definitely the channel will be optical fiber cable, right? Then you see internally, I know that, okay, optical fiber will be chosen. Then you actually have a choice, right? Whether you are going to use, right? I'll write OFC here. What are the types of OFC you have? You can go for, right, single mode or multi-mode, right? Because we know that there is a lot of difference when it comes to the characteristics of a single mode optical fiber with a multi-mode optical fiber, right? What are the difference in general? Let me just lift. One is called as a core size. What is the size of that, right? In general, if you consider it as a if you consider the cross section, what is the what's the diameter? It changes, and refractive index profile will change. Multi-mode will have, right, variable in what you call refractive index, whereas when you consider a single mode, it's same throughout. Maybe then the bandwidth is different, the dispersion is different, the attenuation is different, right? Aperture is different, etc. You see so many parameters you have, correct? So that's why I told proper channel selection is important, right? This was our first this thing. Then the second choice has to be related to the source using which you generate the modulated signal. If it is, say, let's say we use the radio waves or microwaves, let's say, for the communication, what should be the type of antenna? We know that we have a lot of antenna, Yagi Uda antenna, or maybe you can go for the helical antenna, etc., right? What's first option? If it is not, I'll go for RF communication technology, the or the microwave, right? You have like the T type or patch antenna or horn antenna, etc., right? etc. They are also available, right? Again, when it comes to the VLC, the example which we have selected as an example, you have an option to go for maybe LED or laser in terms of the source. Now, what differs, right? What are the different parameters based on which you can choose the LED and laser, right? It depends upon what see, information can be represented in various colors as well. So depending on what color of the light you are going to transmit, right, you may choose variety of light sources as well. So also you can differentiate them among LEDs and lasers. So if you go for LED or if you change it to laser, you are definitely going to change the emission bandwidth, right? And the spectral width of that particular color, right? Maybe color red exists between some megahertz range in case of laser, but it may tend to only kilohertz in LED, right? LED sends red in only some kilohertz range. Okay, bandwidth will vary. Then definitely the output power, laser is very powerful, whereas LED is not so much, right? If you don't want high power, you can go for LED, otherwise this. Similarly, yeah, effective radiating area. If I'm using, say, a very thick fiber, but if I use LED, I might not get the complete illumination pattern for that. So you have to go for laser. So you see, those are the parameters, and also it includes the emission pattern, right? What is the definite in pattern in which it is going to emit? And we have heard of the modes, right? Various modes of communication in case of what you call uh, the optical fiber communication, right? So you basically had 10 mode, right? 01 mode, 101 mode, etc. We have many modes that present. So You choose a mode, and whether that mode is supported by this particular source or not, that is also required over here. Okay, so based on all these parameters, you choose a source. Right. So the next uh, design criteria is that you will choose a specific detector. So again, when it comes to the RF microwave or the radio wave frequencies data sent over there, you have variety of options to design the antennas, right? If you have very less size, you also have options to keep multiple antennas to receive, like radar systems, right? It's not just one single receiver. You have multiple receivers present over there, right? Because you want to go for more accuracy. Increasing accuracy is possible when you use array type of antenna. We have studied that. Okay, so you see those many options you have when it comes to the receiver part, the detector part, when using the RF microwave radio wave signals. But coming back to the example which we have considered, that's a light source. You may have the options such as detectors could be simply pin diode, or you may also have you use the diode which is a avalanche photodiode. These are the examples. Okay, so you can use multiple, but I'll write only two here. Again, what changes, right? What are the differences if I use pin diode versus avalanche diode, right? The first thing is the responsivity, in the sense uh, pin diode will generate an output voltage, right? Even if you have lesser number of photons falling on the active region, whereas avalanche expects more. Okay, until and unless some threshold is met, it's not going to cause avalanche effect, so there is no output voltage or current. So you see, that's a difference, how good it is to respond the number of photons falling on the active region of that particular device. Okay, that's the first thing. Then the second one is the operating wavelength. So if I say operating wavelength, basically I'm talking about whether the operating wavelength of that device falls in the same region as that of the sent uh, signal, right? I'm sending, it's a visible light, but I'm sending, say, green color light. But on the receiver side, if I don't have a receiver diode, photodiode, which detects the green color, then it is of no use, right? So that's what is important, operating wavelength, right? Matching with the supplied wavelength. Then working speed, right? You may have to turn on and off many times, right? So the speed of operation and the sensitivity, right? So small changes, because if you have 1024 levels of data, like starting from message is encoded from 0 to 1023, every change 0 to 1, 1 to 2, 2 to 3 is very minute in terms of the brightness levels, right? So your device should be responsible for that. Okay, only when that is happening, you can do the you can go ahead and detect the signals. Okay, now let's move further. So once you choose, right, the this is again, you're not connecting the you are not selecting the exact device. I said that, okay, I want a source, I'll go for LED since the distance is less, or I will go for a laser, distance is more. I will use a avalanche photodiode, right, for this thing. Only that's the overall rough design. Okay, so far we have done that because this meets general requirements as of now. So in the next level of the design, right? So we have to do a small analysis, right? So that is by using what is called as the link budget, and the you do an analysis of a link budget, and you do another analysis called as raise time budget. Okay, so the next procedure is to perform two types. Okay, two types of analysis. So the first type of analysis is the link power budget. The analysis related to the link power. Okay, so when it comes to the link power, we are basically looking at the power margin, power margin calculation. Again, this is very specific. The power, how much power is required, how much power is lost, how much out of which how much you lose, how much information will be lost, etc. Between the transmitter and the receiver, you have to consider the attenuation, and if you are using some boosters in the middle, I have a lot of distance is huge, right? The single transmitter receiver will not work, means in the middle you might put some connectors, or you may use a booster circuit, or etc, right? So everything needs some power, right? So every power calculation is included in this. This is the link power budget. So basically, when I come to, for example, I'll continue with the example which I consider, that's the optical fiber. Right. I know that I have a transmitter. This is the transmitter. So inside the transmitter, I have some optical source, right? Like some diode. This actually emits the energy. Right. This energy will be coupled by a coupler on this side, right? So you have certain connectors associated with this, right? Again, it covers some distance. You have something like a splice coming into picture, then like that it actually travels quite a distance. Then you might use some connectors, right, etc. Like it travels and it will reach on the other side where you have the receiver, and receiver will have, actually the light falls on the receiver. Receiver is actually responsible to pick up the signal. So this is a receiver, like photo detector. Now you see, you have to calculate the power associated with each and everything. So power of this, power associated with the coupler, power associated with the splice, right, connectors, even the fiber cable, right, and maybe the final connector you are going to use here, right, and this one, the detector. So everything, the power has to be calculated accurately for each and everything, right? So you have something like there is one general equation which we use irrespective of what type of link budget we are using. Okay, whatever is the type of the link, we use a particular uh, equation. This is the transfer, how much should be the transmitted power. This is the general calculation. Ptx is equal to the received power you expect, Prx, plus Cl, plus this is Ms. All right, so where the, this is the safety margin, right? How much additional power I am supposed to add so that there is a safety, right? Then the Cl basically deals with the channel loss, right? Prx is the sensitivity of the receiver, and the PTX is the transmitter power, right? So actually we calculate the, what you call, the channel loss using variety of parameters. Basically, by default, any channel you choose, there is what is called as a path loss. The signal travels 1 meter, means some amount of energy is lost from the signal. That is definite. So when it comes to the optical fiber, the same thing is called as a fiber loss. Okay, so I can write a CL using the length of communication into alpha. Alpha is what is my path loss. In case of fiber, I will call it as a fiber loss. Okay, L is the length of the link which you are trying to communicate, and plus I can have an alpha for CON, that is all the connectors and other elements. Like you may use a booster circuit that loses some power, etc. That's all connectors in the middle. If you use something that actually takes place of that. Okay. So plus some more alphas will come. It might, so some other optional elements will come. I'll write as a K, right? That K basically depends on what is the type of channel you have chosen, right? For example, if you use the light or the OFC for the communication, you have splices coming. That splices will not come if you use radio wave communication. So this K is a variable, right? This is a variable loss component. So L is the length, alpha is the path loss, right? Etc. Right? Like that, we have various losses to be considered whenever I do the power analysis. Ultimately, I will decide how much power is required at the transmitter side. So that is the overall idea behind this particular analysis. Okay, then the second type of analysis is called as the rise time budget analysis. Rise time budget. Now, this actually, it's a time-based analysis. It basically talks about how much response time needed or to be given, right, or to be considered, so that you get the total propagation time, right? Because each device will take certain time, certain response time, right? So this is going to deal with the calculation of the temporal response of each and every system component. Each and every system component takes some time to respond to its input. So it means we know that the system design considerations must take into account the temporal response of the system component. This is obvious because temporal response is directly related to the pulse dispersion, for example, right? Or the bit rate, right, of the channel, right? So if your pulse spread a lot, right, it means something, right? Your bit rate might get reduced because you may give spaces in the middle, right? Because we know one thing, I'll come back to the basics now. So we know that if I send two symbols like this, after say 100 kilometers, if you don't use any repeater, they might look like this, right? So this is the dispersion. Pulses get dispersed. So what you do after 100 kilometers, let me say I don't want to use any repeaters. So what I do here is that I try to separate them while I transmit. So that means that makes their signal to look like this. There is no overlapping, so they are still, you are able to detect them. Okay, so but the thing is that, so you see, this was high bit rate. This is lower bit rate. I gave more space in the middle, right? I gave space between the bits I transmit. So bit rate, etc. All those parameters of your communication is decided by these aspects, like the time of response. In the sense, how quick. So if you use a device which is quick enough to respond to your inputs, right, you may go for high bit rate, right? No problem. But if a device is very slow to respond to your input, right, you cannot give a high bitrate input signal, because when the bit changed, it is still not able to respond to that because it is still in the process of responding to your previous bit. All right. So under such conditions, right, this particular design analysis comes into picture. Okay. Now, then we will try to write an equation for this. This is the general, again, this is a general equation for doing the rise time analysis of any system. So T SYS is equal to, this is T uh, transmitter, Tx square plus Tf square uh, plus we write the Trx square to the power half. It's a root of something. Okay, so the Trx is nothing but the total time required by the components you used inside the transmitter. Okay, square of that, right? Maybe it will come in some microseconds, right? Normally, and even on the receiver side, you have the similar value coming up. So the largest component that might come is, this is from the channel. Okay, this is the, actually everything is rise time only. This is the rise time, okay, of the components of the receivers. Okay, this is the rise time of the components you used in the channel. Like you use many repeaters, you used many connectors, etc. Means you have a huge time that is being that will come as a TF in this case. Okay, that's why our intention is to use as many, as lesser components as possible. The number should be very less, right? Whenever you try to use some repeaters in the channel. So this is the same thing, the rise time of the transmitter side. Okay, so one more aspect that decides the rise time of this is the encoding you use, right? Maybe you used there is a difference in terms of the rise time when it comes to what is a format I have used. For example, if I use a return to zero format, right, that might be a smaller rise time, that might yield a smaller rise time for a given component when compared to the usage of NRZ. Okay, so this is an example, just an example, right? It might vary, right? So for one particular coding format, the rise time might be lesser, other format it might be higher. So I might also have to choose the particular format for encoding, exactly dependent on uh, what is the maximum delay or maximum rise time I can get, right? So depending on that, we have to do these two analysis. Once this is done, then we will look for, then we'll do another analysis. This is actually called as the power penalty. Right, this is actually something like you do a re-verification of whatever you have done so far. Plus, in addition to that, you also do the uh, power calculation, something like you keep some extra power that is required to overcome or eliminate the effect of undesirable system noise, right? So this is, power penalty is definitely required to eliminate, the effects of the undesirable system noise plus distortion. Right. So what are the, what why do you need that this extra power? This extra power is required to overcome noise and distortion, such as the first one is a dispersion, right? So second one could be reflection, right? Many components, whatever power you send to them, they will reflect back, they will send you back, right? So if the reflection rate is say 10%, right? First component will pass only 90%, right? In that 90%, second component will reflect back once again it's 10%. So what will pass? So zero point 0.9 into 0.1, it's 0.9%. So 81% will follow that. So you see, out of 100, second component onwards, you get only 81% of the power, right? So that's why you need more power. Calculate everything. Okay, out of my 10 components, if I want 100% to reach on the other side, I should send at least this much, right? So that is a calculation which you are going to do in the power penalties analysis, right? Then whenever we use multiple lines for communication, right, it may be a two-wire communication or something like that. When you use multiple wires all together, because of the conductivity issues and because you are using conductors, there is a magnetic field around the conductors, because of all those unwanted things. So you can see that there will be what is called as a crosstalk. So it's because of the fields, right? Various types of fields, you have a crosstalk between the wires, right? So that is also an unwanted distortion, right? And maybe if you are using light, then definitely there is another key aspect called polarization, right? What type of polarization you use? There will be polarizers just to maintain the oscillations in a particular direction. So because of that, you lose some power, right? So all these, right, whatever we discussed so far, com- they are the major issues that you need to consider to overcome, right, in the penalty power penalty section. Okay, so overall, what we can say here, in order to design a link, right, specifically, you have to consider the system's performance parameter at the beginning, then go one level below and select those specific, what you call, transmitter, receiver, etc. Then come one level below, do an analysis of link power, then do an analysis in terms of the power, right, raise time, etc. Then do the penalty section, right? All these things, once you finish, you will be able to come to the final design of the link.